So to prove Parsevals' theorem, we are going to start out with the left-hand side of the theorem, right? Integrating psi star x times some general phi of x. And we're going to work on massaging this particular expression and seeing if whether or not we can get it to come into this form where it becomes the integral over k of the corresponding Fourier transforms. So that's the question we're asking. We don't know if that's going to be true yet or not. But what we do know is true is the following statement. I'm going to work on massaging this, and I've got to somehow get my psi tildes and my phi tildes into my expression. And one of the best ways to do that is to realize, well, I know how to express psi of x in terms of psi tilde of x. So let me insert that here. So I'm going to insert in these square brackets my expression for psi of x. And psi of x I know is just the Fourier transform of psi tilde. So it will be the integral over dk of psi tilde of k times then the properly normalized pure state of momentum, e to the ikx over square root of 2 pi. So that will give me psi of x. I also have to include phi of x. So let me put another bracket for that. Phi of x, it's the same thing. Integrate over all possible wave vectors, the corresponding momentum representation for the function, times once again the pure state of momentum, which needs to be properly normalized by my definitions of these quantities. Now here we are about to see why I chose this factor of 1 over 2 pi to appear in this forward transform, which is what then made me have to choose the 1 over 2 pi in the inverse transform. The reason why I split up the factor of 2 pi that we needed into symmetric square roots of 2 pi will become clear very soon now. It's precisely for what's about to follow. Now, our job is to work with these integrals, but as I've said, the first thing you do whenever you insert one integral into another is you want to think very carefully about your integration variable. So let's think about this dk, right? This integration variable, it really only exists within my square brackets. It only exists to take on all possible values from minus infinity to infinity so that I can sum up my integral, and then it has no meaning outside of this bracket. So I have to make sure then that that sort of temporary variable isn't being confused with the variables outside of the bracket, such as this x variable for this dx. But dk is a different name from dx, so that doesn't present a problem. I also inserted the integral that you see here. Once again, this k is a temporary variable for carrying out this integration. But this is a different temporary variable, or technically called a dummy summation index, from the k on corresponding to what's inside these brackets. So to avoid any possible confusions, I should give this another name from the other k, so I will call these here k prime. Okay, now I'm safe to begin to evaluate this integral. One of the first things I should contend with is dealing with this complex conjugation. We always want to get things down to their simplest possible forms before we really start doing heavy manipulations. So this star, I'm going to circle it to remind myself I'm thinking about it. Now, for this complex conjugation, you know what that means. It's just representing a change in basis from plus I to minus I. I have to go in this expression and flip all the possible values of I that I might see. There are no i's in integral of dk. There could be imaginary numbers in psi tilde, so I better make sure to flip all their signs, and the way I remind myself of doing that is I would put my star on that psi. Next, there's no size in 2 or pi or the square root of 2 pi or in the k or in the x or in the e, but there's definitely an I here, so that I has to have its sign flipped. And by this point, I've actually flipped the signs on all of my i's, so I can get rid of this outside star. I can check it off. I took care of all of those. Now, we need to massage this expression. And just like before, I could think about some integration by parts. I don't see any derivatives, so clearly I want to switch my orders of integration. And remember the basic rule. I can switch the orders of integration and the orders of all of the factors in here at will any way I want. If I run into mathematical difficulties, I will introduce a physics convergence factor, but barring anything like that, which really doesn't create any fundamental issues for us, as we've discussed. The only other thing I have to make sure of is that any factor appears always to the right of the summation that refers to it. So if we think about our options then, I want to massage this so it's an integral on dk. So I clearly want to get a dk integral out front. Oh, and of course, I guess while I'm at it, we've got those constant factors of root 2 pi. Let's pull those out together. So I have a nice 1 over 2 pi. As I said, I want to switch things so my dk integral comes first. I don't need to keep writing these minus infinities to infinities. Those were just reminders for our discussion of what that k meant. Now, as soon as I write the integral dk, I probably better put the factor there that has to be in front of it. So I'll put my psi star of k. My next factor involves this x, and I'm integrating over dx, but I notice I've got another factor way over here that has x in it. I want to combine these two factors, so it sort of makes sense to hold off on this x integral as long as possible and combine those x-dependent factors at the very end. So let's keep moving. We did the 2 pi. Now I'll have integral dk prime. And once again, integrating dk prime, I probably should right away put the function that depends explicitly on it so that I make sure that it appears to the right of it, dk prime. Now I've got again an x-dependent factor, so now is the time. I've only got these x-dependent factors left. I better put the integral over all x, and then I have e to the minus. Both of these terms have a factor of x, so I will factor that out, minus ix. The first one is k, which gives me minus ixk. This is a plus k prime, which I can generate by a minus k prime on the inside. So now I've simply rearranged my integral, and now I notice something very interesting. This integral here should look very familiar to us. Technically, we might introduce a physics integration factor, but we've already had that discussion. We know already what the answer to that integral is. It was at the very beginning here of the lecture. It's an integral in the form of some integrand times e to the minus that integrand times another value. And notice it comes with a 1 over 2 pi. There's a 1 over 2 pi down below, so that will work out perfectly. So that integral I have below, I can replace then, combining with the 2 pi, with just a Dirac distribution, where the distribution is written as a function of u, where u is whatever is multiplying my integration variable in my exponential. So let's go down and see then what we have. Taking a good look at this, I notice it looks like what we're looking at here is I've got this 1 over 2 pi factor, which I can combine with this integral, right? And I know the answer to this. That is just going to give me then a Dirac distribution delta of infinitesimal width, right? Because I'm imagining my convergence factor here. Or we just now can automatically make this replacement. And now my integration variable is x, but that's just some dummy integration variable. The answer to the integral is the delta of whatever is multiplying the integration variable. So this will be delta of k minus k prime. So that takes care of that first integral. And notice my 2 pi's have now completely gone away. If I didn't have these root 2 pi's, this would not have happened, and then I wouldn't have a nice simple expression that doesn't have any other crazy normalization factors. So this is why precisely I made that choice. Now, what's next to do is this integral on dk prime. Very conveniently, the integral on dk prime is just a smooth function times a delta function. So we know, we've discussed how to handle this. As a function of k prime, this delta function has its peak when k prime equals k, and otherwise the delta function gives me 0. So the values of phi tilde are irrelevant except very near to k, and very near to k I can replace phi tilde of k with just its value at the location of the peak, which is phi tilde of k, because of this delta function. And now this is a constant factor, phi tilde of k, and I can take that constant factor then and move it outside of my integral, and then I'm just left with the integral of the delta function. So a lot's going on here. So let's write down where we are in case we're losing track. So we have integral dk. The 2 pi went away, as I had said. Then there was psi star of k. And I've just now pulled out phi tilde of k, which is very nice looking. And what I'm left with then is an integral on dk prime of just a delta function. This last integral just gives me, of course, the area under my delta function. The integral under that delta function, of course, always gives me 1. So that's just a factor of 1. And look at this. Lo and behold, what I have is just the inner product of psi tilde and phi tilde, just like I was hoping for Parsevals' theorem. So if we want to translate this into inner product notation, on this side of the equation, I just have the inner product of psi tilde with phi tilde. And of course, what I started out with was the inner product of psi with phi. Either way you want to look at it, as integrals or as inner products, we have proved now Parsevals' theorem, which is what we needed to prove, so that now we have perfect normalization factors. We can forget about proportionalities now. We know exactly how to calculate probabilities in X and in K, and also in general, perhaps then for other observables, and then that will be very useful for us in also many further possible formal manipulations.